And I'm Dezhi Wang, and I'm from Purdue ECE. I'm currently the postdoc. I had my PhD at Duke University with Professor Qinghua Liu. And I will present some of my work on this forward modeling of 3D electromagnetic scattering problems in complicated backgrounds. So I will use this so-called the volume integration method hybridized with domain decomposition method, or VIE-DDM, to do this forward modeling. So I will talk about two fast solvers. One is based on this fast Fourier transform, and another is based on the low-rank approximation. So electromagnetic methods have been widely applied in our geophysical exploration area, and especially like in this mineral ore detection, oil gas reservoir detection, or the tunnel detection. We just discussed a lot, and it can be conducted on the land, and also in the on the plane, and also in the marine. And for all these problems, the simulation of the signal field is very important from these anomalies. And so that's why we propose to, that's why we have to discuss these fast solvers. We will discuss about this VIE. So first, what is VIE? We're all familiar with this kind of scenario with anomalies buried on the ground. So we have a source here, and this source will generate the incident field, and this incident field will further induce eddy current inside anomaly because of this conductivity difference. And this eddy current, we can treat it as a secondary source. And this secondary source will further induce this scatter field in the whole space. So which is what we want to find. So in the volume equation method, this scatter field or secondary field can be obtained simply by doing the Green's function multiplied by this eddy current and do the integration. Actually, this is also a convolution. So then this total field is a summation of this incident field and the scatter field. And then we can use this to form this integral equation. After discretize it, we can find this matrix form, this gamma J and EI. This gamma is actually basically is from this Green's functions integration, and this first term, and this J is a vector that discretizes J, and this E is the discretization form of this incident field. So this linear system can be solved with direct solver and iterative solvers. So usually for large scale problem, we use iterative solvers. So volume equation method has some advantages over this very common differential equation methods like finite difference and finite element methods. First, it can simulate the scatter field directly. Like for the FDN and FEM, they usually solve for the total field, and VIE only need to match this object, this anomaly directly, only match this small region, while the differential equation methods need to match the whole calculation domain. And also with same mesh, VIE has higher accuracy than the differential equation methods. However, this matrix, this J matrix, this coefficient matrix gamma is fully dense. So for large scale problem, it will have very high memory and time consuming, which makes this method not efficient. And also another limitation comes from this Green's function. For our EM problem, the Green's function only have an explicit form for layer media that limits this method. This VIE method only work for the layer media. Some of the improvements have been made. So we know this Green's function. It has so-called the shift invariance property. And therefore, this gamma matrix can be formed as a topic matrix, which can be solved using this VIE. Can be solved where the FFT can be used to calculate the matrix vector multiplication in the iterate solver. However, this improvement only works for objects in the same layer, but not efficient for large-scale problems. So for all these kind of problems, the traditional VIE FFT does not work very well. So first is large-scale problem, which we encountered a lot, like hydraulic fractures. In this case, so it will generate a very dense mesh and make the method not efficient again. And another one is for this kind of problems with objects crossing layers or interlayers and with special geological structures, where the Green's function cannot find the explicit form or cannot use the FFT. So that's why we propose this VIE-DDM. So in VIE-DDM, we first have this kind of original complicated scenario, and have a lot of anomalies. So first, the anomalies or objects are split into subdomains based on their features, and then the volume equation is applied to each of the subdomain, and then we combining all the VIs together and solve for the eddy current inside each domain. So here, if we use the iterate solver, the matrix vector multiplication is applied block by block. So here is the formulation, as we just mentioned. So first, for each subdomain, we apply this integral equation, and then combine all the equations together and form the matrix form of this kind. We can observe that these diagonal terms, they are actually the interaction between the cells. So the 3D FFT can still be used for the matrix vector multiplication. However, for the off-diagonal matrix, 3D FFT does not work, since in this direction it's not convolution. Since if they are not in the same layer, then it's not convolution. So the shift invariance property does not fit. But in the XY direction, if the mesh is the same, then it's still the shift invariance property still satisfies. Then we can apply the 2D FFT at the XY direction for the matrix vector multiplication. So in this case, we can here I show results using this method, which is the scenario of the marine control source electromagnetics. So in this case, we have a very large salt dome and submarine fault and a relative thin oil reservoir. So first, as we mentioned, we split these objects into 7 subdomains, and you then use our methods. So with our methods, compiled with the commercial software console, multi-physics, so we can achieve the error as low as 1.7% with and it's much more efficient. So then we analyze the memory and time cost with respect to the cell numbers. Here we analyze the XY direction and Z direction respectively. Since we for the 2D FFT, we only use at XY direction, not Z direction. So we need to discuss them separately. So as can be seen for the XY direction, so it's here. So when the NZ, the cell number in Z direction is fixed, the XZ change, we can observe the memory is approximately linear dependent on the cell numbers. The time dependence is approximately the order of n log n. However, when the cell number in the Z direction changes, both the dependence are approximately quadratically. So which this is because the Z direction we do not use the FFT. So which makes this method does not work very efficiently for the case when the meshes in the Z direction is very dense. So that's why we propose this low rank approximation used for this matrix vector multiplication. So in this method, the off-diagonal part, we still keep use 3D FFT, which is efficient enough. However, for the off-diagonal matrices, we observe they are rank deficient, where if the objects are separated away. So we can use a low rank approximation for this matrix vector multiplication. So in the low rank approximation, the rank deficient matrix can be expressed as the product of two low rank vectors, and then the matrix vector multiplication becomes this kind of form, and which is makes the memory and computation complexity both linear. So here we will use this popular adaptive cross approximation or ACA method for this low rank factorization. I will skip the details. So here is the performance of our method. The same case as previous one, 5 objects in different layers. We compare this memory and time cost. As can be seen, if the z direction cell numbers is fixed, both methods have similar performance for the memory and time. However, when the cell numbers in z direction changes, we can observe that for the low rank method or this VIE-ACA, both the memory and time cost are dependent on the dependence of this both memory and time is linear, is fully linear. And however, for the previous method, is both. I'm sorry. Yeah, the memory cost is linear, but the time cost is order n log n. But for the previous FFT-based method, both are nearly quadratically. So this low rank method is much more efficient. So here's the performance of the method. So as can be seen, for a large scale problem, as can be seen, we have 2 large objects and 1, 2, 3, 4, 5 very thin sheets. So as can be seen, these sheets, they have the maximal size difference about 600 times. And this kind of difference, we cannot use the FFT-based method. And we compare our method with the commercial software FACL using the SIE. So we can see our method can achieve the error under than 2% with more than 1,000 times more efficient. So this is a conclusion. So the EM scattering problems with complex and homogeneous objects in multiple layers, which are difficult to tackle with the traditional VIE FFT method, can be treated accurately and efficiently with the algorithm we proposed. And to overcome the bottlenecks of the FFT-based method, the low-rank approximation method is used for matrix vector multiplication, which is more efficient and can deal with the large-scale problem efficiently. That's all about my sharing. Thank you so much. If you have any questions, happy to answer.